I'm Dr. T, and welcome to my home office. Today I'd like to talk a bit about enzymes. So enzymes are proteins that are also catalysts. So these are proteins that will do chemistry. And this is essentially how chemistry is done by the cell. So for these guys, if we're thinking about biochemistry, this is the biochemistry, effectively. So the way proteins, or I should say enzymes, work is that they're going to be a protein. They bind to the substrate, which in other areas of chemistry we would call the reactant, but in this case we're going to call it the substrate. And so this is going to be a molecule that they're going to start doing chemistry on. And to be honest, it could be substrates. It doesn't have to be just one. Now, enzymes are going to have a very specific shape to them, and they're going to have a very specifically shaped pocket in them. This is called the active site, and this is where the substrate or substrates actually go. When the substrate or substrates go into the active site, the enzyme is able to change its shape a bit, and in the process allows those substrates to have chemistry done on them, and thus they become the products. And bada boom, bada bang, we have some chemistry. Now, enzymes, because of their very high shape dependency, are only going to be doing chemistry on a fairly narrow subset of substrates. Try to say that 10 times fast. Now, some enzymes have a larger variety of substrates that they can work on. Other enzymes are specific to one molecule and one molecule only. And that's actually pretty much the norm. One or two molecules is all they can work on. Now, if you're thinking, okay, so I can do one chemistry on one molecule, I can do a lot on that molecule. No, typically it's only a small amount of chemistry. So it's only moving one or two bonds, maybe doing basically one chemical reaction, nothing too elaborate. In order to get to these elaborate chemical reactions, like taking sucrose all the way down to carbon dioxide, it's not going to be one enzyme. It's going to be dozens upon dozens of enzymes in what we call a pathway. So an enzyme pathway is basically the cell version of an assembly line, although usually they're not actually in a line. There are cases where they are. It's kind of more like an artisanal goods. You know, one person makes leather, another person makes shoe soles, another person takes shoe soles and makes them into shoes, yet another person makes shoelaces, that kind of thing. And the enzymes are doing the same basic idea. One enzyme takes one atom off, the next one moves one from one spot to another, the third one takes the one that just got moved off, and so on and so forth until you get yourself your final product. Now, no discussion of enzymes would be complete without talking about enzyme regulation. Cells have various ways of regulating their enzymes, turning them up, turning them down, either by simply having more or less of them, or by modifying the enzymes in one way or another. Additionally, there are other ways of controlling enzyme activity, specifically inhibitors. These are typically small molecules that will bind to enzymes, and the enzymes don't work as well. These may be permanent bindings, what we call irreversible inhibitors, in which case the enzyme is broke and the cell has to recycle the enzyme. These, of course, are very potent. Alternatively, you can have reversible, I should say. We have the irreversible. You could have reversible, where the inhibitor binds to the enzyme, but it comes off, so the enzyme's not able to do its job as well. These inhibitors might bind to the active site, what we call competitive inhibitors, or they might bind someplace else, what are called non-competitive inhibitors. This idea of enzyme inhibition is basically the core of most pharmaceuticals. If you think about drugs such as penicillin, these are irreversible inhibitors for a particular enzyme required for bacterial cell growth. Since we're not bacteria, they don't hurt us. Penicillin has no damage, but it is absolutely lethal to bacteria. Likewise, irreversible inhibitors that do target our enzymes can be very deadly, such as the ones in the death cap mushroom, a very aptly named fungus. Of course, reversible inhibitors are quite common. This is the spring in the south, so we have lots and lots of pollen, and lots of us will be taking inhibitors to inhibit our immune response to said pollen, so the allergies are at least somewhat controlled. These are reversible inhibitors. Obviously, you wouldn't want these to be irreversible. And hence, most of your pharmaceuticals are some form of enzyme inhibitor once again, most, not all. So that's a brief overview of enzymes. With that said, have a wonderful day.